In this lesson we'll see a few details about vector notation. In specific, we'll see what we mean by Cartesian components, unit vectors, position vector, how we represent a force, moment of a force, and a couple. To begin with, we'll see what we mean by Cartesian components of a vector quantity. Okay. For that, consider a force P bar which is acting as shown. For this force, we can consider that it is consisting of three components: component along x-axis, component along y-axis, and component along z-axis. Okay, and name each one of them by the coordinate along which the component is considered. That is, this component we call it as px bar. This component we'll call py bar. This component we call pz bar. Okay, the idea is that given this vector p bar can be written as the vectorial sum of the three components px bar plus py bar plus pz bar. These three are called Cartesian components when the coordinate system x, y, z we considered is a right-handed system. What we mean by right-handed is when you stand here on the positive z-axis and look down onto the xy plane, the smaller angle between x and y, okay, when it is swept, it goes in counterclockwise direction. That is, if you move from one point on x-axis along an arc to a point on y-axis, you'll be going in counterclockwise direction. If that is happening, we call it a right-handed coordinate system, and these we call Cartesian components. Further, if we define angles, let us say we define angles cos alpha as angle between p bar and x bar. So it is defined by px over p. Px is the magnitude of px bar, p is the magnitude of p bar. Similarly, if we define cos beta as the magnitude of y component by the total force, if we define cos gamma by magnitude of z component by the force, these three quantities, cos alpha, cos beta, cos gamma, they are called direction cosines. If we specify cos alpha, cos beta, cos gamma, that is direction cosines, the direction of this p bar is completely specified. Okay. Further, we can very clearly see the relation cos square alpha plus cos square beta plus cos square gamma is equal to 1. That is because magnitude of p whole square is equal to px square plus py square plus pz square. Having seen what we mean by the direction angles, which are alpha, beta and gamma, direction cosines, which is cos alpha, cos beta, cos gamma, we'll try to see the next topic, that is what we mean by unit vectors. Okay, by unit vectors, again we mean three vectors which are going along a right-handed coordinate system: I bar, j bar, k bar. I bar along x, j bar along y, and k bar along z. These vectors, when we deal with displacement vector, this I bar, j bar, k bar will be displacement unit vectors, and they carry a unit 1 meter or 1 centimeter, whatever it is, 1 unit. When we deal with unit force vector, this I bar, j bar, k bar will represent 1 unit of force, so that they carry a unit of Newton. Once we understand that a force F bar we can represent as Fx I bar plus f y j bar plus f z k bar, where this fx, fy, fz, those are components, scalar components along x, y, z. We note that this fx or fy or fz, they can be either positive or they can be negative depending on the orientation of the force. If the force is oriented in a negative direction along x, this fx can be negative. Similarly, fy, fz, they can be either positive or they can be negative. Once we see this unit vector, we'll try to see what we mean by a position vector. Let us consider one point P in space in a Cartesian right-handed coordinate system. Let us say that its x coordinate, y coordinate, z coordinate are x1, y1, z1. Then we define position vector of the vector P as P bar, as the line going from O to P, OP bar, and this we can see is x1 I bar plus x2 j bar. Sorry, let me correct it. x1 I bar plus y1 j bar plus z1 k bar. Similarly, if you consider another point Q here, okay, and Q bar can be written as a line segment which is going from origin O to Q bar, OQ bar, as x2 I bar plus y2 j bar plus z2 k bar. These are two position vectors P bar and Q bar. Now let us say we have a situation where a force of some magnitude F is acting along a line going from P to Q. Let us represent this as force F bar, which has a magnitude of F, and line of action goes along 2 points P and Q. For that, we first write down what is the vector PQ bar. PQ bar is a vector going from P bar to Q bar. That we write as Q bar minus P bar. This directly comes from the triangle law. This you can simplify as x2 minus x1. You have x2 here, x1 here, multiplied by I bar, plus y2 minus y1 bar multiplied by j bar, plus z2 minus z1 k bar. Okay, this represents the vector PQ bar, which is going from P bar to Q bar. Now you can find what is the length of this vector. Length of the vector PQ bar is sum of squares of the components under square root. That is, you can write this as x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. This is the length of the vector PQ bar. Once we find the length of the vector PQ bar, we can find a unit vector going along PQ bar. This will be your PQ bar by magnitude of PQ bar. So given the values of x1, y1, z1, x2, y2, z2, we can form what is PQ bar. x2 minus x1, y2 minus y1, z2 minus z1 in I, z, k directions, and length we can find by a very familiar formula from coordinate geometry, and then you can find what is the unit vector. Once you find the unit vector also, then you say representation of the force F bar which is going along PQ is its magnitude multiplied by the unit vector going along that direction. Once we see this, we can now see what we mean by moment of a force. Let us say you have a force F bar going in any direction. Let us say this is the line of force of F bar and with a direction indicated F bar, and you want to take moment about a point, let us say A. We know from our scalar notation that if you want to find the moment of the force, you drop a perpendicular from A onto any point on this F bar, measure that perpendicular distance and multiply magnitude of the force by perpendicular distance to find the moment of the force. But the notation in while dealing with vectors is slightly different. In vectors, from point A you will draw a line to any point on the line of action of force. You can draw to a point M, or you can draw to another point M1, or to any other point M2. As long as these are M1, M2, they are lying on the line of action of force, it is enough for us. You can draw a line from point about which you are taking moment to any point on the line of action of the force and call it RF bar. We are using the subscript R to say that this is the position vector from point A to any point on line of action of force. So RF bar is position vector from A. This is the point about which we are taking the moment. Then we can say that this moment M bar is M bar about point A. Strictly speaking, it should be about an axis passing through A, but when we understand that, it's okay, which is RF bar cross F bar. We have seen how to represent force F bar. We have seen how to represent position vector RF bar, and we know what we mean by this cross product. When we do this, we will see that this M bar is a vector quantity which is perpendicular to the plane formed by RF bar and F bar. Once we see the moment of a force, we can now see what we mean by a couple. Okay, a couple is two forces which are equal in magnitude, opposite in direction, and parallel to each other. When once a system of forces is simplified to this stage of a couple, it cannot be further simplified to get a single resultant. Sometimes this couple is also called a wrench. Okay, a property of this couple is that you can take moments of these forces about any point, a point A here, or a point B here, or a point C here. Okay, you take moment about any point, moment of these two forces forming a couple, the moment is going to be the same. Let us try to illustrate that. Let us try to show that in a little more detail. Let us say you take one point A here, okay, and you draw a position vector from here to the line of action of the other force. Okay, this we can call RA bar. Okay, okay, now we can write the moment M as M bar as RA bar cross minus F bar. Okay, we need to carefully note that the moment arm is RA bar, which goes from point about which we are taking the moment to any point on line of action of the force. The force is minus F bar here, so we wrote it as RA bar cross minus F bar. Okay, the reason why we chose this point A to lie on one of the forces is we don't have to consider what is the contribution of this force F bar, because point A is lying on the line of action of F bar. Similarly, you can consider, let us say, point B here. Okay, and consider a position vector to any point on line of action of force F bar and call it RB bar. So, and write this moment as RB bar cross F bar. So whichever way you do, either this way or this way, the moment is going to be the same. Okay, if you have two forces which are equal in magnitude, opposite in direction and parallel, we call it a couple, and the moment due to a couple we can evaluate either as this formula or this formula. We'll try to solve a couple of problems which use these concepts in vector notation in subsequent lessons.